Chapter 30 notes. Parts of an atom. Protons and neutrons in the nucleus are called nucleons. In naming the atom, Z is the atomic number. That is the number of protons. It also tells what atom number it is. A is the atomic mass number. It's the total number of protons and neutrons, so it's the number of nucleons. And N would be the number of neutrons. So number of neutrons equals the atomic mass number minus the atomic number. This is a template for our atom here. We have X would be the atom symbol, and then it's A over Z. For a common carbon atom, carbon 12 looks like this. It's 12 over 6. Isotopes are atoms that have a different number of neutrons, a different N. It makes our atomic mass different. So here are 4 isotopes of carbon, and our mass is measured in 3 different units: U, kilograms, or MeVs divided by C squared. U stands for Unified Atomic Mass Units, and this conversion is on your AP formula sheet. You'll be using it quite often in this chapter. 1 U is 1.636 10 to the minus 27 kilograms, which is 391 MeVs. Nuclear forces. Next topic. The strong force holds the nucleons together. The electric force repels like charges. Those protons in the nucleus want to repel each other, and it's the strong force that holds them together. A strong force only works over small distances. As the nucleus gets larger and larger, that strong force gets weaker and weaker, and so there's a limit to how big an atom can be. The electric force works over any distance. The farther and farther and farther away, the weaker and weaker that force is, but the force always exists. Binding energy. There's a table on A12 in your book we'll be using for several of our homework problems. This is the difference in mass of the nucleons minus the mass of the complete atom. For example, a helium atom has 4 nucleons and 2 protons. So we add up 2 protons, 2 neutrons, and 2 electrons. All of those pieces add up to this amount of mass. However, a helium atom weighs less than that. So this difference in mass is called the mass defect, and this represents the binding energy that holds all those particles together. So I'm taking that difference in mass, I can convert it into kilograms, and then use Einstein's equation E equals mc squared to calculate how much binding energy there is for that atom. And this would also be the energy released if we bust it apart. Changing to electron volts, we divide by 1.6 times 10 to the minus 19. And since these numbers are so large, we're going to change it to mega electron volts. So that would be 28 mega electron volts, MeVs. Now we have a shortcut for this process. If we take that and use that first conversion I showed you, all we're doing is multiplying by 931, and we get that same number, 28 MeVs. Nuclear forces. The larger nuclides, the Coulomb force overpowers the strong force, causing instability. As the nucleus gets larger and larger, the strong force gets weaker and weaker and becomes unstable. Radioactivity is when these unstable nuclides of isotopes break down and eject particles. There's 3 types of radioactivity. First one is alpha particles. Alpha particles are a helium nucleus with a positive 2 charge, so there's no electrons. A beta particle is an electron, and this is ejected from the nucleus. It's not part of the orbiting electrons. And gamma radiation is high-frequency electromagnetic waves. It's not a particle. Transmutation is the changing of one element into another. So as a radioactive atom decays into a different atom, we call that transmutation. This picture is showing all 3 of those radioactive particles coming out of our sample in the lead block in through a magnetic field. The beta particle is curving to the right, and we know charged particles move in a circle in a magnetic field. Using a left-hand rule, you can see that the force on that particle will be to the right. The alpha particle is curving to the left. Using the right-hand rule, you can see that that force is to the left. The gamma ray has no charge to it, so it's unaffected by the magnetic field and goes straight. Our next picture is showing penetrating power. Alpha particles can't even make it through your skin. The beta particles can make it through your skin but not through your body. And gamma rays can go through nearly everything. They're extremely dangerous. So this is our general formula for alpha decay. We need to have this formula memorized and be able to apply it to any atom that's given to you. The starting atom is called the parent atom, and what it decays into is called the daughter nucleus, or the daughter atom. And then there's the alpha particle, which is a helium atom. Example, radium-226 will decay into what? So I'm going to start with radium-226, and I have to look up which atom number that is. That's atom number 88. And then looking at our sample at the top, on the X prime it says Z minus 2, so I'm going to subtract 2 from the 88. And for the atomic mass, I'm going to subtract 4, so I'm going to get 222. Now we have a rule that's conservation of particles. The top numbers all have to add up to the same thing on both sides of the equation. The bottom numbers have to add up to the same thing on both sides of the equation. All right, then I can look up atom number 86 is Rn. Now the helium has a positive 2 charge because there's no electrons on it. And we also have a conservation of charge. That means the other atom needs to have a negative 2 charge. And the reason for that is the number of electrons from the initial radium is 88 electrons, and so the Rn also has 88 electrons, so it has 2 extra electrons. Special note, A is always conserved and charge is always conserved. For beta decay, a neutron turns into a proton plus an electron and a new particle called an antineutrino. It's a massless, chargeless particle. So sample here, carbon-14 is going to decay into what? So on the bottom, it's carbon-6, and if we are changing one of our neutrons into a proton, we're going to have an extra proton, so it's going to go up to a 7. Atom number 7 is nitrogen. And the 14 on the top is the sum of neutrons and protons, and since we lost a neutron and gained a proton, the number still stays the same. It's still 14. This nitrogen will have a positive charge because the initial carbon had 6 electrons with it. So does this nitrogen. It'll have 6 electrons, so it's missing an electron. So this is the general formula for beta decay. The symbol for the antineutrino, the anti part is the bar over the top, and the symbol for a neutrino is the Greek letter nu. Now this one is the formula for beta plus decay, and that E plus is called a positron, and this occurs if there's more protons than neutrons. What's going on in beta plus decay is a proton turns into a neutron instead of a neutron turning into a proton. Notice that this one produces a neutrino, not an antineutrino, and it makes a positron instead of electron. Gamma decay gives off gamma radiation, which is electromagnetic waves with a very high frequency. This is our general equation for that, and notice that the A and the Z stay the same. What we're changing is from an excited state into a normal state. The excited state is called an isomer. Isomers can occur through several processes. If they get hit with a neutron, a nuclear collision could excite our atom, or sometimes during beta decay, it could go through an extra step and make an excited state, or the isomer. Here's a diagram I got from the book of showing how a beta decay can go 2 different routes. It can go straight from the B12 to the C12, or it can do an intermediate step and have the isomer in between. Notice that this energy level diagram is similar to the electron energy level diagrams, except these aren't actually orbiting shells. They just draw it as the diagram to help us understand the energy levels. And also notice that these transitions are measured in mega electron volts, where the electron transitions are measured in electron volts. End of part 1.